That's a comment of the machine, not of you. Can you see? Yeah, that's it.
Was it F5?
F5.
Yeah, F5.
Started.
You know what they say about all PowerPoint for apps?
Yeah. Well, you know the story of why I got converted into PowerPoint?
I opened like...
Yeah?
I went to India, and I went to this ashram. Free holiday, it was sold out.
Thank you.
And I thought, I know free holidays, it means you've got to do some work somewhere. And
it doesn't really feel all
missing.
What's this?
The resolution problem.
why is that? Do we know?
Yeah.
Do we know why, Nick?
We do.
Okay, look, I knew there was some reason for inviting you, Nick.
That was play.
No, it was at this ashram, you see, and they were having a conference, and they had this guru who had some very deep insights, so to speak. And he was going to reformulate general relativity using these basic ideas. I'm not even going to mention what the ideas are, because they're so good.
Where are the control panels on here?
And at this meeting, which I wasn't supposed to say anything, they asked me to introduce, to open them. They asked me if I would give a lecture for an hour, and they asked me if I would sum up at the end and say what a great conference it's been, and so on. That was my free lunch. Well, when it came to my presentation, what I had was the old-fashioned transparencies. And I said to the guy there, have you got an overhead projector?
And that's
And I thought,
standing out there.
oh, they haven't even, you know, I'm really in a primitive place. And he says, didn't you bring a PowerPoint presentation with you? So I sort of, whoa, then it was my turn.
Really primitive.
Yeah.
And then it was my turn. And they even said, well, give us your transparencies and we'll convert it to a PowerPoint.
Excellent.
And I'm afraid that really got to me. And as soon as I got back to the UK, I started PowerPoint. Thank you, Nick. PowerPoint presentations. Oh, great. Okay, well, fitting in with George's idea, what I want to do is to give the general philosophical background and then do some details. Okay? And I'm titling it rather pompously. It's a process idea because I want to get away from particles and fields in interactions in a given space-time, or a given space-time. And I want to start with the process basis and to show how some of these ideas are reflected in some of the things that people are doing with non-commutative geometry. But when I'm using non-commutative geometry here, I'm using it in a very loose sense. I'm not using it in any specific sense. It's the sort of thing that Freddie and I have talked about. Is there really a non-commutative geometry or not? But it's sort of a catchphrase to... Okay. So, the problems that I see, the problems that seem to me to be the really outstanding challenges in physics in particular, is reconciling quantum mechanics with general relativity. But also there's a second one, which we're not going to talk about today, which of course is understanding the relation of matter and mind, which is something that Roger Penrose has been spending a lot of time on in the last few years, trying to bring physics into that very, very general, very deep discussion. Now I want to just concentrate on the quantum mechanics and general relativity, and I want to try to get across David Bohm's idea of looking for new orders in physics, and how does that fit in? Well, in GR, it essentially continues the classical tradition where you have locality, where you have continuity, and you have determinism. And what I mean by that is that there are particles assumed, something that Malcolm and I were talking about just the other day, particles assumed here, and they follow geodesics. When you come to quantum mechanics and you look just at the particle aspect of quantum mechanics, of course you get non-locality, you get discontinuous jumps, and you get indeterminism. So how different the two orders are straight away. And the non-locality, although that came out in the work that David and myself did on analysing the quantum potential with John Bell made a tremendous contribution here. It really was in the older work of Niels Bohr, where he was talking about wholeness. The wholeness of the experimental, to describe the phenomena, you have to include a specification of the experimental setup. But he didn't want any of this. He didn't think it was possible to find some underlying continuity deterministic theory under. But in fact, we know it can be done, and that's the work that the group at Birkbeck, many of the research students have been doing. You can make a theory which is completely consistent with quantum mechanics, where particles follow trajectories, and that's the bone theory, or the bone mechanics as it's called. The only thing I don't like about using the word bone mechanics is that it's not mechanical. It's more organic. If you really look at the quantum potential and ask yourself, now what is it actually doing? You find it turns out to be much more organic than mechanical. And one of the things that leads to that is a non-mechanical, but it's really the wholeness idea that gives this non-mechanical background to it. And even in 1951 in David's book, he talks about the term quantum mechanics is very much a misnomer. It should perhaps be called quantum non-mechanics. So even without looking at the quantum potential, Dave had this idea that quantum mechanics was more organic. And this was in his book, which was reckoned to be one of the better books at that time on quantum mechanics. And then of course, what I got bogged down in is the squabbles about interpretations. And I've got a list of interpretations with ... I mean, almost as many interpretations of quantum mechanics as there are people working in it. And for this reason, I've come to, there must be something, I don't know why we keep defending these things, there must be something wrong somewhere. Something deep that we're not getting clear if we can hold all these different interpretations. What's happened? Did it change? Oh, I'm going backwards, sorry. Okay, so then the question is, well, if you're going to rule out the idea that you want to start with either particles or fields on an a priori space-time interacting with each other, where are you going to start? The question then is, what is basic? Well, we've got two seemingly contradictory things. Relativity is telling us all is geometry, and quantum mechanics is telling us no, it's more to do with Hilbert spaces and perhaps in a more refined form of C-star algebras. I'm still sorry, I'll get used to it in a minute. It's these new gadgets, these newfangled gadgets, you know. But of course you've got in here, that one of the reasons why I don't like this idea of an a priori given space-time is because quantum gravity already suggests that there's some kind of quantum space-time. I thought I put some inverted commas on quantum space-time in quotes. And even now, it seems that people are now catching up what David and I were discussing in the 70s. But this is a quote from John Byers in 2004. Quantum mechanics will make more sense when we regard it as part of a theory of space-time. In other words, that's bringing quantum mechanics back into the geometrical picture again, trying to find a geometrical structure for it.